In the previous section, we used the LabVIEW FPGA project template to create a LabVIEW FPGA project. By the end of this module, you'll be able to describe aspects of FPGA technology. Okay, so now let's start Lesson 3, Programming using LabVIEW FPGA. So first we'll start off with a quick introduction to FPGA again. Then we'll talk about how do you develop the FPGA VI. We'll talk about how to use interactive front panel communication, and then we'll go to selecting an execution mode where we can figure out, do we want to execute on the FPGA or do we want to simulate it? Then we'll go to compiling the FPGA VI and what happens in that process. And then lastly, we'll talk about some basic optimizations that you should use as best practices when you're programming FPGAs. So in this slide, we have the FPGA layout and components. So we talked about this a little bit before, but just as a review, on an FPGA chip, there's a couple of different things. So one is going to be your configurable logic blocks. So those are the things that are actually going to be doing the logic functions. So it's going to be doing processing, calculations, and things like that. Another thing that we have on there is the programmable interconnects. And what these do is they route different logic blocks together, and they basically do this to create the functionality that you define in software. Not only do the programmable interconnects route signals from logic blocks together, they can also route them in and out of I/O blocks to get signals into and out of an FPGA. So how does the FPGA work? Again, the programmable interconnect switches and wires route signals between various hardware resources in an FPGA, and this is how it essentially implements the logic that you've defined in software. So hardware resources on the FPGA include things like logic gates, flip-flops, block memory, multipliers, things like that. So if you want a more detailed description of how each of these FPGA components works, you can look at the link shown on this slide. So in this slide, we have an example of a visual example of how FPGA works. So let's say we're creating a VI, and then that VI is trying to calculate a value for f from inputs A, B, C, and D, where f equals A plus B times C times D. So if we look at the FPGA here, we can kind of get a high-level overview of what's going on. So let's say we've got those inputs. So you have A, B, C, and D, and you have those signals coming in through there, through an I/O block. And then those signals are routed to logic blocks on the FPGA, where it's going to actually implement the addition and the multiplication. So then these are all routed, and eventually the result of that signal is routed to another I/O block where it outputs the signal F. So you can see how on the slide the logic of whatever program you're writing is actually implemented into hardware, and there is no OS running here. So let's take a look at some of the benefits of using LabVIEW FPGA. So if you're using LabVIEW FPGA, if you know how to use LabVIEW and also learn a couple of the things specific to programming LabVIEW FPGA that we talk about in this course, you don't have to learn VHDL or Verilog. You can simply use LabVIEW to program the functionality of your FPGA. And if you have something on an FPGA, then you're going to have true parallel execution. And we'll talk about that a little more in the next slide. And then also, because the FPGA is implemented in hardware, it's going to be very reliable and very deterministic. So here we see an example of true parallel execution on an FPGA VI. So notice that we've got two separate things going on, truly in parallel. So if we look at the top one, we've got signals A, B, and C coming through, and we're doing some sort of algorithm on that, and it's going to get output to F. Then we look at the bottom, we've got X, Y, and M coming in, and those are being implemented in a totally separate algorithm, and that's going to output to Z. And if you take a look at that, when it's implemented in hardware, in this case, these two algorithms have no dependencies, so they can run totally parallel to each other. So because it's being done in hardware, this is true parallelism. These two things are really happening on the hardware at the exact same time. If you wanted to, you could add even more things, and as long as they don't have any dependencies, then all those things are happening in parallel. You can have 10 things going on in parallel. Whereas before, if you're working on a computer with an OS, then there's only a certain amount of parallelism you can get. You can only get as many parallel things going on as compared to how many CPUs you have. So one big advantage of FPGAs is you're having these things implemented in hardware, and they are executing truly parallel to each other. So here we see that the FPGA is connected to I/O resources, and it's also connected to a bus that allows the FPGA to talk to the host, or the host to talk to the FPGA as well. So if you take a look at this, If you look at the I/O resources there on the right, for every I/O resource that you have, part of the FPGA resources, so part of that FPGA hardware needs to be used to implement that communication with your I/O. And then similarly, on the bus side, part of your FPGA resources need to be used in order to implement that bus interface where the FPGA can communicate with the host. And then after that, the rest of the FPGA you can use for timing, processing, triggering, calculations, and things like that. So just know that part of that FPGA has to be used for the bus interface and also to communicate with I/O. So let's look at some of the timing benefits of FPGAs. So let's take an example of a multi-loop analog PID loop rate. So on FPGA, these loop rates can exceed 100 kilohertz, whereas if you're running this on a real-time operating system, they can only run, about at 30 kilohertz. So again, on the FPGA, you're going to get faster speeds. Also, with a digital control loop rate, you can execute up to 1 megasample per second or even more, depending on the target. On FPGA, there's also this concept of a single cycle time loop. And with those, you can execute things up to 200 megahertz or more, depending on the target and the clock configuration. And we'll talk about single cycle time loops more in a later lesson. Also, as we saw before, due to parallel processing ability, adding additional computation or adding additional loops, it does not necessarily reduce the speed of the FPGA application because all these different loops and computations can be happening in parallel. Now you can describe aspects of FPGA technology. Next, we will add an FPGA VI to a LabVIEW project and view FPGA function palettes. In the previous section, we described aspects of FPGA technology. By the end of this module, you will be able to add a FPGA VI to a LabVIEW project and view FPGA function palettes. Okay, let's talk about developing the FPGA VI. So remember, there is no operating system on the FPGA. When the FPGA VI is functioning or executing on the FPGA, it's actually being executed on hardware. When you're developing an FPGA VI, you can only download and run only one top-level VI on the FPGA at a time. Okay, so there's only going to be one top-level VI running on that FPGA. The FPGA can run independently of the host, so regardless of what the host is doing, the FPGA VI can be running on that FPGA separately and independently. The FPGA VI can also store data in memory using something called memory items and FIFOs, and we'll talk about that later in a separate lesson. When you create a FPGA VI under an FPGA target, what will happen is if you go to the functions palette, it'll populate with an FPGA palette that is specific for FPGAs. Also, when you're developing an FPGA VI, you'll usually use integer or fixed point math to perform calculations. Starting in LabVIEW 2012, single precision floating point is also supported. We'll talk about this a bit more in Lesson 7, Signal Processing. So to add a VI under an FPGA target, you'll want to go to your Project Explorer, and then you'll want to look at where the FPGA target is. So after you do that, you want to right-click the FPGA target item in your project, select New, and then select VI. So once you've created this FPGA VI, if you go to the block diagram and you try to view the functions palette, you'll notice that the functions palette will adapt to show functions that are compatible on FPGAs. So if you take a look at it, there are some palettes that are similar to LabVIEW for Windows. For example, there's still while loops. You'll still be able to do numeric and Boolean functions and things like that. But you'll also notice that there are some FPGA-specific palettes as well. So you'll notice that there's an FPGA I/O palette that's specific to FPGAs, and also FPGA math and analysis and things like that. One example is the FPGA I/O palette. This is a palette on the functions palette that's specific to FPGAs, and in this palette you'll find I/O nodes, which are the nodes that you would use to communicate with I/O through your FPGA. Another palette I want to let you know about is the FPGA math and analysis palette. So on this palette, you'll find FPGA math and analysis functions that are optimized to execute on an FPGA and also use a minimal amount of resources on the FPGA. The functions will typically perform point-by-point calculations. Okay, now let's dive into LabVIEW and take a look at these palettes. Okay, so now we've got a LabVIEW project open, and notice that this LabVIEW project has a CRIO in it, and it also has an FPGA target under the CRIO. Okay, So let's say we want to create a VI to execute on this FPGA. So what you want to do is you want to select the FPGA target, right-click it, go to New, and then select VI. So let me close this real quick. And now we have a VI, and you'll notice that over here on the bottom you'll see that it is executing in the CompactRIO project, and it's also executing under the FPGA target. So let me go to the block diagram, and let me close out of this real quick. I just want to show you guys that this VI, notice that you'll see it right here, Untitled 1, and this VI actually is under the FPGA target. Okay. So now when I go to the block diagram and I go to the functions palette, so if I right click, notice that the functions palette is going to adapt to functions that are supported on the FPGA. Okay. So notice that some things in this palette are going to be similar to LabVIEW on Windows. So notice we have for loops, we have while loops, we have case structures. If you go to the numeric palette, you'll see that you have addition, subtraction, and things like that as well, and Boolean functions as well. Okay. I do want to point out that there are some other things. So let me pin this down real quick. So notice that here we have FPGA I/O. If we go to this palette, notice that we have I/O nodes, I/O constants, and these are the things that you'll use to interact with your I/O. So let's go back to our programming palette. Also, I want to bring your attention to data storage and transfer. So this is something that is specific to FPGA as well. So notice we have registers, we have memory, we also have FIFOs. Okay, so these are ways that we can store data and also transfer data on an FPGA, and we'll talk about this in a later lesson. Another one I wanted to point out real quick is also the FPGA Math and Analysis palette. So let me click into here. And notice that over here there are some algorithms that are built into LabVIEW FPGA. So for example, if you need to do scaled windows or you want to do an FFT, these are things that have already been implemented in this palette. So instead of building your own, you can just use one of these. Notice that the FFT looks a little bit different on FPGA than it looks on a Windows system. So we'll talk about these functions a little more in the signal processing lesson, but I just wanted to show you for now. If you look into here, there's other functions as well. So if I go into the control sub palette, notice that there's already a PID function that's implemented for you as well. So if you need to do PID, you can use this function. All right, let's talk about top-level FPGA VI front panels. Okay, so as we know, with an FPGA, the hardware resources inside it are limited, right? An FPGA is going to have a finite amount of hardware resources. So one thing you need to do when you're programming for FPGA is you want to think about ways that you can try to use the minimum amount of resources that you need. So one way you can do that is you can use the minimum necessary controls and indicators for programmatic front panel communication to a host. So for every control and for every indicator that you put on your top-level FPGA front panel, there has to be some FPGA resources that are used in order to implement the logic of being able to communicate those controls and indicators back down to your host. Okay, so in light of this, you should try to minimize the amount of controls and indicators on your front panel and only use the ones that you need. Sometimes what you can do as a developer is you can add temporary controls and indicators for debugging, just so you can see what's going on inside your program. But when you're done using those temporary controls and indicators for debugging, make sure you remove them afterwards to save on your FPGA resources. Now you can add an FPGA VI to a LabVIEW project and view FPGA function palettes. Next, we will communicate between the FPGA and host PC using interactive front panel communication. In the previous section, we described how to create an FPGA VI and view the functions palette. By the end of this module, you will be able to communicate between the FPGA and host PC using interactive front panel communication. Now let's talk about interactive front panel communication. So remember, an FPGA really has no user interface, right? So the FPGA is actually just hardware. So you have functionality that's happening on that FPGA chip. Okay. So let's talk about a couple things. So to communicate data from the FPGA, you can either communicate from the FPGA through the bus back to the host PC, or you can also communicate by using your I/O lines. The front panel is displayed on your host PC. So when you're creating an FPGA VI and you run it, you're going to be able to see on the front panel some of the values that are coming from the FPGA VI. And we'll talk about this in the next slide. The block diagram that you've created for your FPGA VI, well, that defines the functionality of what you want your FPGA chip to do, right? So if you think about it, the functionality that's defined on your block diagram is actually compiled and it's executing on the FPGA chip itself. Also, there's a communication layer that shares all control and indicator values. So every control and indicator that's placed on your top level FPGA VI, those control and indicator values are being communicated from the FPGA chip back up through the bus to your host computer. So when you're running an FPGA VI on the FPGA, you can't use any debugging tools because it's already executing on the FPGA hardware. So what you want to do for debugging is typically you want to test your FPGA VI first on the development computer. So before you even compile it and send it to the FPGA, you want to just test it targeted at the development computer and make sure all your logic and your algorithms are correct before you go through the trouble of compiling it and sending it to the FPGA. Another thing you can do is if you want to debug the FPGA VI when it's already running on the FPGA, you can add extra indicators on your front panel, and those indicators will give you values, and you can use those values to kind of debug what's happening on the FPGA. So here, let's talk about interactive front panel communication. So on this slide, you see that there is a FPGA VI, and you've got the front panel, and you also got the block diagram. So on the front panel, you'll see that there are controls and indicators, right? So you see a couple of numeric controls. You see some indicators as well. And every control and every indicator you have on there, you can communicate those values between the host computer and the FPGA target over the bus. So if you think about it, the FPGA VI front panel, it's updating with values that are coming from your FPGA. Okay, so you can think of this as your user interface almost for your FPGA VI. And if you look at the block diagram, notice that on the block diagram, that's where your functionality is being defined, right? So the functionality that you've defined on your block diagram, that is being compiled and it's being actually executed on the FPGA hardware. So if you think about it, the FPGA target is actually executing whatever you defined in your block diagram. So this concept of an interactive front panel communication, what's happening is the functionality of your block diagram is executing on your FPGA target, and then your host computer is kind of an interactive way of you being able to see the current values of your controls and indicators. You're able to see what values are being updated on there from the FPGA. Now you can communicate between the FPGA and host PC using interactive front panel communication. Next, we will execute an FPGA VI on either the FPGA target or development computer by selecting the execution mode for an FPGA target. In the previous section, we communicated between the FPGA and host PC using interactive front panel communication. By the end of this module, you will be able to execute an FPGA VI on either the FPGA target or development computer by selecting the execution mode for an FPGA target. Okay, let's talk about selecting an execution mode. So to select an execution mode, what you would do is you would right-click the FPGA target in your Project Explorer window and select Properties, and it'll launch the dialog that you see on the screen. So notice if you click the debugging category, there's two ways that you can execute that FPGA VI. One way is execute the VI on the FPGA target, which is that first option there. Now when you're doing that, if you hit the run button on that VI, what it'll do is it'll compile your code and it'll actually execute that VI on the FPGA hardware. Another thing you can do is instead of executing the VI on the FPGA target, you can execute the VI on the development computer. So if you take a look at that second option, if you're executing the VI on a development computer with simulated I/O, what happens is it doesn't send that VI down to your FPGA. It keeps it on your host computer and it basically uses simulated I/O so you can try to verify the functionality of your VI without having to compile. And we also see a third option down there with execute VI on development computer with real I/O. So you can also have an option of executing that VI on your development computer, so you don't have to compile yet, but you can actually use real I/O from your FPGA target if this happens to be supported on your FPGA target. So another way that you can select the execution mode is you can also right-click the FPGA target in your project and then just use a shortcut menu to navigate to execute VI on, and you can select your mode directly. And we'll see that later on in the demo. So once you've selected an execution mode, you'll see in your project that your FPGA target will tell you what mode it's in. So if we look at the very top one, notice that it says FPGA target, and that's pretty much it. If it looks like that, then what's happening is you're executing your VI on the FPGA target. So in this case, if you're running that VI, it's going to get sent down to your FPGA. If we look at that second item there, you'll notice that it says FPGA target and also says development computer. This tells us that when I run this FPGA VI, what's going to happen is it's going to just execute on my dev computer, and it's not going to be sent down to my FPGA. So this is a very useful mode for you to make sure that all the algorithms and all the logic on your FPGA VI are correct before you go through the trouble of compiling it. So if you're executing your VI on your development computer with simulated I/O, you can either use random data for any FPGA I/O, or you can also use a custom VI for FPGA I/O as well. You can also, on some targets, you can also execute the VI on your development computer and use real I/O that's coming from your hardware. Okay, let's talk about testing with the development computer. So one thing I want to make sure you understand is when you're compiling an FPGA VI, that compilation can take from a few minutes to several hours. So it's something that will take a lot of time. So if you select your VI and you tell it to execute on an FPGA, it's actually going to go through this compilation process, which could take a long time. So that's why it's a good best practice. Before you ever execute your VI on the FPGA and compile it, you want to go in that simulation mode. You want to go and execute it on your development computer instead first. And this way you can make sure that the logic for your VI is correct, right? So if you look at the development flow that's shown at the bottom here, notice that you'll create your FPGA VI. Once you think you're done with it, then simulate that FPGA VI on your PC to test it. And then that way you can use all your debugging tools. You can use highlight execution, you can use probes, you can use single stepping, and that way you can kind of debug your VI and make sure everything looks correct on your simulation before you decide to compile it. Okay, so keep simulating, keep modifying your FPGA VI until everything looks good in that simulation mode. And then once you're done with that and you think everything looks correct and you've done your due diligence, then only after that execute your VI on the FPGA and then go through that compilation, which may take a few minutes to several hours. And that way you'll be able to save a lot of time by going through that kind of a development flow. So at this point, it would be good for you to be able to do exercise 3.1. So if you can, go ahead and do exercise 3.1, and you'll be able to create an FPGA VI and verify the functionality of the VI using the development computer. So you'll be able to get some experience on simulating your FPGA VI before you compile it. So right now, what I'm going to do is I'm going to go ahead and demo this and demo the solution just so you can get a high-level idea of what's going on with exercise 3.1 and also how to execute your VI on the development computer for simulation. Okay, I've opened up the solution for exercise 3.1. So let's take a look at this. So notice we have a CRIO target here, and we have the FPGA target that is under our CRIO. So we were talking about the execution mode. So one way you can take a look at the execution mode is you can right-click the FPGA target and go to Properties. This will cause this window to pop up. And then notice if you go to Debugging, you've got a couple different modes. So Execute VI on FPGA target. Again, if you select this mode and run a VI, then it's going to compile it and send it down to the FPGA hardware. Another option is you can do Execute VI on development computer with simulated I/O. So this is a good option to use if before you compile, because you want to make sure you verify the functionality and make sure everything looks right on your VI before you decide to compile it. So notice that there's two options here. You can either use random data for your FPGA I/O. So if you happen to be using any I/O, it's just going to use random data. Or you can use a custom VI for FPGA I/O. So if you select that one, you can click on the Help button to get more information on that. So for now, I'm just going to leave it as use random data if I use any I/O. So now I'm going to click OK. Actually, I'm going to switch this back to execute VI on FPGA target so I can show you a different way of configuring this. So the other way of configuring this, which is a little faster, is you can right-click on your FPGA target, go to execute VI on, and notice right now it's executing on the FPGA target. Instead, I want it to be executing on my development computer with simulated I/O because I want to test it out first. So I'm going to select this, and notice now that it updates to show dev computer right here. Okay, so in this case, we've got our FPGA target, and someone has already developed a simple math VI. So because it's under the FPGA target, this VI is going to be my FPGA VI. So let me go ahead and double click it to open it. I'm just going to put that here. I'm going to show the block diagram. So right now, notice that it's going to be executing on my dev computer. Okay, so I should feel free to test it and use any debugging tools I want, just to verify the functionality first. So let me go ahead and change this to 3 or 2. I'll change Y to 3, and I'm going to go ahead and run this. So now that just ran on my development computer, my host PC, and notice that x plus y is 5, x minus y is -1, and x times y is 6. So I've verified that it looks like my algorithm is correct, and I'm ready to go. However, let's say I didn't get my expected results and I need to debug it. Well, because I'm running this VI on my development computer, I can actually take advantage of all these debugging tools here. So I can hit highlight execution, hit run, and I can use that ability to debug my VI. I can also do single stepping, I can use breakpoints, I can use probes, and all the other debugging tools that are available to me on Windows. Okay, so this is a huge advantage of making sure you debug and test your FPGA VI on your development computer first. Okay, so now that everything's done, I can go ahead and close this. And if I verified everything looks correct, I can right-click this target, go to execute VI on FPGA target. And once I've done that, when I open this VI and hit run, it'll actually compile it and send it to my FPGA VI. But we'll talk about that a little bit more in the next section. So note how quickly we were able to progress from development to testing, right? We had a VI that we created, simple math, and then we were able to start testing it and debugging it right away just by executing it on our development computer first. So have you ever tried troubleshooting a VI without using the debugging tools? So imagine you were trying to troubleshoot a VI and you didn't have the ability to single step, you didn't have any breakpoints, you didn't have highlight execution, you didn't have any probes either. Now you can imagine that would be very difficult. And the point that I'm trying to make is once you're executing your VI on the FPGA hardware, when the VI is running on the FPGA, you no longer are able to use highlight execution. You're not able to use single stepping because the logic is already running on hardware. So just remember that, and by remembering that, we can remember the advantages of being able to test it on your development computer first. Okay, one is that you're going to be able to verify the functionality and make sure you're not compiling it for nothing. So first, make sure that your functionality is correct, and if it's not correct, you're going to be able to use your debugging tools to fix whatever that problem is before you decide to compile it. In the previous section, we executed an FPGA VI on either the FPGA target or the development computer by selecting the execution mode for an FPGA target. By the end of this module, you will be able to compile an FPGA VI and describe an overview of the compilation process. Okay, in the previous section, we talked about simulating the FPGA VI on the PC to test it out before you compile. So at this point, we've simulated, we've tested it out, and we know that our FPGA VI is supposed to work. So at this point, we can go ahead and compile it. To do that, make sure you set your FPGA target to execute VI on FPGA target. Okay, so once you've done that, you can hit run on the FPGA VI and it'll go ahead and compile it. Okay, so what happens when you compile an FPGA VI? Okay, now let's describe an overview of what's going on here. So if we start over here on the left, notice that we have LabVIEW. Okay, so in LabVIEW, you have your FPGA VI, and let's say we tell it to compile, and we execute on the FPGA VI and we hit run. Okay, So the first thing that happens is LabVIEW will convert that FPGA VI into intermediate files. Okay, so it's going to generate these files like VHDL and things like that, and it'll send it over to the compile server. So the compile server is going to receive compilation requests from LabVIEW, and then it's going to send these compilation jobs to an available compile worker. Okay, so now we're going from the compile server. It's going to send those intermediate files over to the compile worker. Now that we're at the compile worker, that is going to transform these intermediate files into actual binary data that describes how to configure the FPGA circuit on the FPGA target. So the compile worker is actually using Xilinx tools to do this compilation. So once it's done all that, it's going to take that binary data and it's going to send it over back to the compile server. And then the compile server is going to send that binary data to LabVIEW. So once that binary data is sent back to LabVIEW, what LabVIEW will do is it'll create a bit file, which is a .lvbitx file, and that bit file is going to contain the binary data that describes exactly how to configure that FPGA circuit to implement your logic. The FPGA VI will now also have a reference to that corresponding bit file, and that bit file will get downloaded to the FPGA and will reconfigure that FPGA to execute that logic that you've defined in your FPGA VI. So to run an FPGA VI on the FPGA target, make sure you configure your FPGA target correctly. So make sure you right-click it and then you set it to execute VI on FPGA target. So once you've done that, if you open up your FPGA VI and hit run, now LabVIEW will automatically compile it, download it, and run it on the FPGA VI on the FPGA target. Okay, now let's talk about working with build specifications. To compile an FPGA VI, you'll need a build specification. So if you don't create a build specification, when you hit run on that FPGA VI, it'll automatically create one for you. However, you can also create one manually. If you do this, to create one manually, you can right-click build specifications and then go to new and compilation. And then from there, you can select your top-level FPGA VI. And once you have a build specification, there's a couple things that you can do, which we'll talk about on the next slide. So here are some common actions that you would do once you have a build specification. So let's say we've manually created a build specification. What we can do is we can right-click it and we get a couple different options on there. So one is build. If you select build, then you'll compile the VI. Another option you can select is estimate resource usage. And what this will do is it'll estimate the FPGA resource usage without compiling. So it quickly does an estimation, and it'll tell you whether, I guess based on this estimation, it'll tell you whether your FPGA is going to fail or if it's actually going to fit on the FPGA. Okay, so it's kind of a quick way of finding that out without having to go through the whole entire compile process. Another thing you can do is you can generate intermediate files. So if you choose the option to generate intermediate files, one thing that's good about that is it can be useful for catching certain code generation errors. For example, it might catch something like in your FPGA VI, if you're doing something that's not supported, it'll give you an error about that and let you know. Another thing you can do from the build specification is you can display the compilation results. So if you've already built that particular compilation, you can choose this option and you can kind of look at some of the results. So you can see how much space the compilation took up, the speeds and things like that, and get all sorts of specs. Okay, now let's go into LabVIEW and see what the build specification looks like. Okay, let's take a look at the build specifications. So notice in this project, we've got our FPGA target, and we also have a FPGA VI here called Simple Math. Notice that our FPGA target, if you right-click it, we're executing the VI on the FPGA, so it'll actually be targeted and run on the FPGA. If I was to open up Simple Math and hit the Run button, because there is no build specification defined already, it would automatically create one for me. However, in this demo, what I'm going to do is I'm going to manually create a build specification just so we can take a look at some of those options. So if I go to Build Specifications, if I want to manually create one, I would right-click it, go to New, and then Compilation. So once I've selected that, it's going to pop up a window for me. And here I can do a build specification name. So I'm just going to leave it as My Compilation. One thing you want to do is first you want to go to source files, and you want to go to your top level FPGA VI. So in this case, my top level FPGA VI is Simple Math. Okay, I'm gonna put that over here. And notice that this is set as the default build specification. What that means is if I was to run Simple Math VI, it would compile it using the information that's defined in this build specification that I'm creating right here. Okay, now I'm going to click OK. And notice now that I have a build specification for Simple Math. Okay, so once I have one of these build specifications, if I right click, I do get a couple more options. So like we saw in the slides, if I click Build, this will actually compile that VI. Another thing you can choose is Estimate Resource Usage, and this is a useful way to find out quickly, without compiling, whether or not your FPGA VI will actually fit on the FPGA hardware. Another thing you can do is do Generate Intermediate Files, and what this does is it'll try to generate some of those intermediate files, but in that process it'll tell you if there's some errors in your VI, such as using unsupported objects. And then if you've already done a compilation with this build specifications, you can click Display Compilation Results. And what that'll do is it'll show you the report that's on the compilation, and you can view a lot of different specs such as timing and how many resources it used and things like that. So again, if I had opened Simple Math and there was no build specification already for it and I hit run, it would have automatically created something and it would have popped up over here. In the previous section, we compiled an FPGA VI and described an overview of the compilation process. By the end of this module, you will be able to describe the various stages of the compilation process. Okay, let's talk about the different stages of the compilation process. First, we'll start with Generate Intermediate Files. Here's where LabVIEW will convert the FPGA VI into intermediate files such as HDL code and send it to the compile server. The next step is queuing. Here's where the compile server will queue the jobs and send the intermediate files to the compile worker for compiling. The next step is HDL compilation, analysis, and synthesis. This is where the compile worker transforms intermediate files, such as VHDL code, into digital logic elements. The next step is mapping. During mapping, the compile worker divides the application logic between the physical building blocks on the FPGA. Next, we have placing and routing. The compile worker assigns the logic to physical building blocks on the FPGA and routes the connections between the logic blocks to meet the space or timing constraints of the compilation. After that, then we'll get to generating the bit stream, and this is where the compile worker creates binary data that LabVIEW saves inside a bit file. And then lastly, we've got the bit file creation. And this is where LabVIEW saves the bit file in a subdirectory of the project directory, and from there you can either download or run that application on the FPGA. Okay, so when you're compiling your FPGA VI and you have your FPGA VI up and you click Run, the first thing that's going to happen is it's going to start generating intermediate files. So this window will launch, and in the meantime, it'll take that FPGA VI and start generating the HDL code for it. So one thing to remember is once your compilation starts, do not edit your FPGA VI. Okay? Once you've created your FPGA VI and start compiling it, it's compiling it for that instance of the FPGA VI. So you want to make sure that the compilation finishes and you test it. If you were to start compiling your FPGA VI, and then in the middle of the compilation, you go back to the FPGA VI and start changing it and saving it, then that compilation no longer is associated with your new instance of your FPGA VI. So the takeaway here is once you start compiling your FPGA VI, don't make any changes to it until you've finished testing the actual compiled FPGA code. The last bullet here says you can create a compilation queue by starting another compilation while the first one is still running. So if I was to open up an FPGA VI and then hit run, and then my compile worker is already working on that first FPGA VI, I could take another FPGA VI and hit run, and what that would do is it would queue up that compilation. And you could queue up several different VIs, and then the compile worker and server will handle queuing those up and will handle the order of compiling those VIs and sending the information back. So after LabVIEW is done generating those intermediate files, it will pop up the compilation status window. So from this window, you're going to be able to look at different reports. So To look at a specific report, you would just go to the reports item in this window and select the report that you want to look at. So as the FPGA VI is compiling, you'll have more and more reports available as the time passes by. You also have the option to close this window, so you can either just close the window and have it still be updated with the compilation status. You can also disconnect this window from the compilation status, even though the compilation is still happening. Or you can also have the option to cancel all compilations as well. So if you were to cancel the compilation, it would tell the compilation worker to stop compiling and basically cancel it. So those are the three options there. Usually you can just minimize this window and just keep it running in the background, and you can check up on it and see when your compilation's finish. And if you want any more details on this particular window and different options within it, just go ahead and click the help button, and that'll bring you a nice help file with detailed information. So in the compilation status window, there is something called the configuration report. So let's talk about that. In the configuration report, you'll see different pieces of project information. So for example, you'll have the name of the project, the name of your target, and also the top level VI name. It'll also tell you what the start time of the compilation was, in case you want to keep track of that, and some other things as well. So essentially it'll give you the Xilinx compiler configuration for the FPGA VI. Another report that's available in the compilation status window is the device utilization report. So there's actually two times that this report will show up, and one is generated at pre-synthesis and the other one is generated at the synthesis stage of compilation. And what this will tell you is how much of your device is actually being utilized. So for example, what percentage of your FPGA resources need to be utilized in order to implement your FPGA VI. So if we take a look at this window over there, you can see that there is a table here for device utilization, and you'll see use, total, and percent. So if you look at the percentage, and that percentage is something that's very close to 100% or even above 100%, then that's telling you that your FPGA VI is using a lot of the logic on that FPGA, and it's probably going to fail the compilation. So ideally, that percentage that you see there would be something safely below 100%. So another report that we can look at is the timing report. Again, there are two separate versions of this report as well. One is going to be generated at mapping, which is kind of the estimated values, and another one will be shown at the placing and routing, which is going to show you your actual values of timing during compilation. So the thing to look at here is, if you see here, there's a requested column and there's also a maximum column. So the maximum column is showing you the rates, the maximum rates that your code could possibly attain. And then under requested, that's the rate that your code is actually trying to attain. So ideally, the requested column would be something that is less than or equal to the maximum column. Now, if you're trying to request a rate that is higher than the maximum can be, then your compilation is going to fail. Another report that's available is the Xilinx log report. So this is going to include detailed Xilinx log information, and if you're familiar with Xilinx tools, you could possibly use this report to do some debugging yourself. Otherwise, it's there for your reference, and you can also save that to a file. There's also a compile worker window, and this window will show up wherever your compile worker is installed. So by default, that's going to be on the same computer as your compile server and also on the same computer as your LabVIEW development environment. So notice that on the Windows taskbar, there is an icon there, and if you select that icon, it'll show up a window for the LabVIEW FPGA compile worker. And one thing it'll tell you is the server connection status. So it'll tell you, is my compile worker connected to the server right now? If it's not connected to the server, it's not going to be able to compile anything. Another piece of information that is useful is the jobs. So under jobs, it'll tell you which exact compilation it's currently working on. So this is a way of being able to see what your compilation worker is actually doing. So at this point, exercise 3.2 would be a good exercise to do. In exercise 3.2, you basically are able to take an FPGA VI, you're able to run it, and then start that compilation process and see that for yourself. Right now, I'm just going to go ahead and demo what you would see in this exercise. In exercise 3.2, what you're going to do is you're going to take your FPGA VI and you're going to execute it on the FPGA and have it compile, and then you'll be able to look at the compilation process and look at the reports that are associated with it. So first thing we want to do is make sure our FPGA VI here, Simple Math, has been tested, which we've done already. And to compile it and execute it on the FPGA target, we want to make sure that we right-click here, go to Execute VI on, and make sure that it's on FPGA target. So we have that selected. Now what we can do is we can open up our FPGA VI. In this case, it's Simple Math VI. And we're going to run it. So once we click Run, it's going to ask us, okay, well, where do you want to compile it? In this case, we're just going to use our local compile server, which is on the same computer, and click OK. Now it's generating the intermediate files, so it's creating the VHDL files or HDL files, and it's going to send those to our compiler. So now what you're seeing is our compilation status window, and what we're going to do here is we're just going to go ahead and let our compile worker do the compilation. And you can see in the status what step it's in. Over here, we'll see our reports. So if I click on it right now, you'll notice that it's done the pre-synthesis part already, so I can look at these reports as they're generated. And then at any point, you can also go to the Xilinx log just to get an idea of what's going on. And if you are familiar with Xilinx tools, the text there should make sense to you. So for now, what I'm just going to do is I'm going to sit here and we're going to wait until the compile to finish, and then we're going to look at the reports that are associated with each stage of it. Okay, now it looks like our compilation completed successfully. So it launched our FPGA VI, in this case it was Simple Math, and it ran it right away. So this VI, it's not running in a loop, so it basically just does some calculations and spits out the answers. So just to show you, let me try changing some of the values. So I'm going to change X to 2 and Y to 3, and then I'm going to hit run. So when I hit run, this is actually going to be sending it to the FPGA, and this code that we've developed for Simple Math is actually executing on our FPGA hardware. So let's hit run. Notice it said preparing for interactive execution. So it's taking these values from my host computer, sending it down to the FPGA, and the FPGA was able to send back these values. So notice that X plus Y, 5, X minus Y, -1, X times Y is 6. So looks like our logic is correct. Okay, so let me minimize this VI and let's take a look at our compilation report. Okay, so notice that the status is complete. Right now, we're looking at the configuration report. So here in the configuration report, we have available right away at the beginning of our compilation. It tells us, our project. It's telling us the build specification. It's also showing our top-level VI, Simple Math, things like that. Okay. So if we go to the reports, let's go ahead and jump to summary first. So summary is what's going to show up at the very end, and it's going to give us a summary of our compilation. So it's going to tell us that our compilation completed successfully. Notice that's going to give us our device utilization. So this is going to tell us what percentage of the FPGA resources we used in our compile. So notice that here is 2.6%, 4.0%, 2.5% of these particular elements. So it looks like this didn't take up very much space on our FPGA. Let's see, and we have timing also. So it's going to tell us whether we were able to achieve the timing requested by our VI. And it's also going to give us our compilation time. So in this case, this VI took about 5 minutes to compile. And it tells us how long each section or each stage of that compilation process took. Okay, so let's go through the different reports. So these reports will be available to you as the stages of the compilation process complete. So when pre-synthesis is done, this will show up and you'll be able to look at it. When synthesis is done, you'll be able to take a look at this report. When mapping is done, you'll be able to look at these two reports. And when the place and routing is done, you'll be able to look at this report. Okay, so these will become available to you as the stage is complete. In this case, we've already finished the whole compile process, so we can look at any of these reports. So let's go to estimated device utilization pre-synthesis. So over here, we see a report of our device utilization after it's doing its pre-synthesis. So it's kind of an estimate of how many resources or how many FPGA resources this VI is going to take. So notice that we're using some slice registers and slice LUTs. In this case, we use this many, and out of this total that's available on our FPGA. So we're only using 4% and 4.5%. Okay. Let's go to the next one. And here we have device utilization after the synthesis stage. So this one will be a little bit more accurate and closer to our final percentage. So notice over here we got 2.9 and 4.2. So usually on these, what you want to look at is the percentage. If the percentage is really close to 100%, if it's like 100% or greater, then that's telling us our compilation might fail because there might not be enough resources on our FPGA to implement your logic. One thing I want to say about the percentage though is the percentage doesn't necessarily, so if the percentage is at 50%, it doesn't necessarily mean that that what you have, if you double it, it's going to reach all the way to 100%. The way that the Xilinx compiler works is as it gets closer to full, so as it gets closer to maybe 90% and higher percentages, it'll start working hard to make things more optimized. So when it's going along at first and it sees that it has plenty of space, it's not going to work as hard to make everything totally optimized on the FPGA, just because that way we save time and we don't have to have a really long compile just to optimize something when it's going to fit anyways. So just wanted to let you be aware of that. So let's go to final device utilization after mapping. So after the mapping stage, we're going to see what our final utilization is. So notice that we've got 2.6 here, 4.0, and 2.5. So it looks like in the final utilization, it used another element here, which is a multiplier to make things a little bit better. Let's take a look at our estimated timing. So after the mapping stage, we see that these are different elements or components of our FPGA VI, and these components are requesting these speeds. And it looks like our maximum over here is greater than what we requested, which is a good thing. So if you want to take a look at the requested column here and make sure it's less than the theoretical maximum that that component can run at. So it looks like we're safe here. Everything here is less than the maximum that's associated with it, so the compile should have no problem completing. So that's going to be our estimated one. After the placing and routing stage, we can look at our final timing, and it looks like in the final timing, our requested is still less than our maximum, so it looks like we're good to go. And then here the Xilinx log. If you're familiar with Xilinx tools, you can kind of go through this log, and this will update as your compile is happening, and you can kind of see exactly what the Xilinx compiler is doing. Okay. And I'll just go back to the summary page, and you'll notice on the summary page we have that summary of pretty much everything that happened. Okay, so let me close this. And notice that we were able to run our simple math VI on our CompactRIO, and we've got the IP address there where it was where CompactRIO was on the network for the IP. And notice that it automatically generated a build specification. The other thing I wanted to show you real quick before we're done is I'm going to the folder where this where my project was. So when I first opened the project, there was no FPGA bit files subfolder. When I compiled this and it finished compiling, remember in the compilation stage, what happens at the end is it generates a bit file that describes how to configure the FPGA circuit to implement your logic. So if we go inside the FPGA bit files folder, notice that we've got a file called something.lvbitx. So the lvbitx file extension is what represents a LabVIEW FPGA bit file. So this bit file is going to be sent to our FPGA, and that's how our FPGA knows how to configure itself to implement your logic. Okay, let's go through some discussion questions. So what is the benefit of having reports generated at different points of the compilation? So what's the benefit of having, the estimated utilization show up first, and then the final device utilization, and then the estimated timing and things like that? Well, one of the main benefits of having reports generated at different points is you can early on kind of see if your compilation might fail. So for example, if you're able to look at the device utilization, the estimated device utilization very early on, and it's something very high, it's something way greater than 100%, well, in that case, you might want to just cancel that compilation because there's a high chance that it'll fail, and then you can go back to your FPGA VI and try to modify it and make it more optimized and use less resources, and then start up that compile again instead of going through that whole entire compilation process just to see it fail. Let's look at the next one. What if you had not tested on the development computer and the VI did not function as intended? So this is something you definitely want to think about now before you start developing. If you think about it, if I create an FPGA VI and then I didn't check whether the behavior was correct and I just went and compiled it, maybe it takes an hour to compile. Well, after an hour and it finished compiling and I run it, and then I see that I made a mistake in my programming and I didn't have the right logic, well, I basically wasted that entire hour of compiling when I could have caught that much earlier. Now, if I had tested that VI on the development computer first and hit run, I would have noticed right away that the behavior was incorrect. And I could have just used my debugging tools and corrected it within minutes, right? And then once I know that everything is correct and the behavior is what I intended it to be, then I can go ahead and compile it. And then after, that hour compile or however long it takes, then now I'm just troubleshooting whether it fit on the FPGA. Okay, let's look at the last question. What if your compile fails? Well, if your compile fails, well, this is a good launching point for the next couple of slides and also some of the things that we talk about in the next lessons. What could cause a compile to fail? Well, one, there might not be enough FPGA resources to implement what you're doing, so you might have to optimize that. Or maybe it's not going to meet your timing requirements, and there's ways to help fix that. So we'll talk about that for the rest of the course. Now you can describe the various stages of the compilation process. Next, we will describe various considerations when compiling an FPGA VI. In the previous section, we described the various stages of compilation. By the end of this module, you'll be able to describe various considerations when compiling an FPGA VI. In this slide, we see a couple of FPGA compilation considerations. So we'll talk about each of these bullets in the coming slides. So let's talk about what causes a recompile. So when you run an FPGA VI that LabVIEW has already compiled, LabVIEW does not need to recompile if the VI does not have any non-cosmetic changes. So if I have a LabVIEW FPGA VI and I've compiled it already and I haven't made any changes to it, if I hit run, it'll go ahead and execute the compiled FPGA VI and it won't have to recompile it. Also, if I make a change that is just cosmetic, so for example, if I was to rearrange the front panel and all I did was move my controls and indicators around, and that's all I did, if I hit run again, because I haven't made any actual logic changes to it, that VI is not going to have to do another recompile. However, if the LabVIEW FPGA does have a non-cosmetic change, then LabVIEW is going to recompile the VI on the next run. So for example, if I change something on the block diagram, like if I change an algorithm, then next time, if I save it, next time I run it, it's going to have to recompile because something has changed. Also, if I add or delete functions on the block diagram, or if I rename a controller indicator, because that name changes, it's going to have to change the way that it sends it over the bus and associate it with a different name. So in that case, I'll have to do a recompile next time I run that VI as well. Or if I add a new control or add a new indicator and I save the VI, then when I hit run, it's going to have to recompile the VI. Okay, this slide is talking about how to compile an FPGA VI remotely. So by default, when you install LabVIEW FPGA and you're compiling your VIs, LabVIEW FPGA, the compile server, and the compile worker all reside on the same computer. However, if you want to make things more efficient, sometimes what people will do is they will install the compile server and the compile worker on a remote computer. And maybe that remote computer has a lot of resources. It'll be able to compile things faster. So this way, they don't use the resources on their development computer. And what happens there is when I hit run, it'll send our compilation to a remote computer to handle the actual process of compiling it. And that way you save some of the resources on your own development computer. So if you want more details on the exact steps for that, you can go to the Compiling an FPGA VI Remotely help topic in the LabVIEW help. Other things you can look into is there's also something called the LabVIEW FPGA Compile Farm Toolkit. And if you're using this, what that'll do is you can have multiple developers send compilations to a compile server, and that compile server machine will handle sending all the different compiles to multiple computers that all have compile workers on them. So in that case, because there's multiple computers that are handling the compile, you can have multiple compilations going on in parallel, which will save a lot of time. So if you want to create a farm system for compiling your FPGA VIs with multiple developers, that's another route to go as well. Another thing you may want to look into is the LabVIEW FPGA Compile Cloud Service. This is a way of offloading your FPGA compilations to a high-performance, high-reliability cloud server to reduce the compile time of your LabVIEW FPGA VIs. So those are just some options you have for compiling your FPGA elsewhere besides your development computer. Here we describe the two causes of a compilation failure. So one would be timing. So for example, if your FPGA VI is asking for some timing, maybe you're asking for a loop rate that is higher than what your FPGA can implement. In that case, the delays in the design circuit exceed the period of the specified clock, and your FPGA compile will fail because it couldn't meet the timing requirements. Another reason your compilation might fail is resource utilization. So in this case, your design requires more FPGA resources than are available on the FPGA. So the way you've written your FPGA VI, the FPGA itself did not have enough resources on it to implement your design. So when your compile fails, those are the two things that you would have to go back into your FPGA VI and try to fix. And we'll talk about ways of fixing timing and also trying to make your FPGA VI more efficient on resource utilization in the rest of this course. On this slide, we see some of the Xilinx compiler options. So the way that you get to this window is you would go to your build specification, and then you can right-click it, and then go to its properties. So if we take a look at this window here, what you should usually have enabled, which is enabled by default, is that Use Recommended Settings item there. So when that is enabled, what Xilinx will do is it'll use recommended settings based on whatever target you're setting your FPGA compile for. So this is the recommended item to select, so I would usually just go ahead and just use the recommended settings. However, there's other design strategies you can use if you want. So if for some reason you need to use one of these different design strategies, you can disable the Use Recommended Settings item and then choose one of these. So some other design strategies that are available to you are minimum compile time, or you could try to make the compile, try to optimize the timing performance. So if you're failing your timing and things are getting really close, you can try to optimize for timing. And you can also try to optimize for area as well. There are other custom things that you can do as well on this window, but in general, you should just use the recommended settings. Now you can describe various considerations when compiling an FPGA VI. Next, we will describe basic optimizations you should implement as basic programming practices for all FPGA VIs. In the previous section, we described various considerations when compiling an FPGA VI. By the end of this module, you will be able to describe basic optimizations you should implement as basic programming practices for all FPGA VIs. So in this section, we're going to talk about basic optimizations that you'll want to make on all FPGA VIs, and these are just kind of best practices that you should do. So the ones that we're going to describe are relatively easy to implement. They shouldn't require any major changes in your code architecture. They should be basic programming practice for all FPGA VIs. And these optimizations that we're talking about in this particular section primarily affect FPGA size. So these optimizations will help your FPGA VI use less FPGA resources. So here we see the types of basic optimizations that we're about to talk about. So we'll talk about limiting front panel objects on the top level VI, how to use small data types, and how to avoid some large functions. Okay, so let's talk about limiting front panel objects on a top-level VI. So each front panel object on your top-level VI must have logic to interact with your host VI. So every control, every indicator is going to consume a decent amount of FPGA resources because it's going to have to implement logic on the FPGA to be able to send that information from the FPGA to your host. So the less front panel objects that you have, the more resources you'll save. So in general, only put controls and indicators on your front panel, on your top level front panel, and limit to only the ones you need. Each read and write from the host to the FPGA is broken down into 32-bit packets to transfer across the bus. If you have something that's greater than 32 bits, then it'll have to be broken down into 32-bit packets and transfer those across the bus. So consequently, arrays and clusters with more than 32 bits are going to require an extra copy on the FPGA to guarantee all the data is read or written coherently. Another optimization that you'll want to do is you want to limit front panel arrays. So in general, you should avoid using arrays on the front panel, but if you have to, you need to make sure that all arrays are a fixed size. And the way that you do that is you can right-click an array and then go to Set Size, and then that'll allow you to make that array a fixed size. So a compilation is going to fail if the array size is larger than the available FPGA resources. Arrays can quickly use large amounts of FPGA resources, and the reason for that is because each bit in the array uses its own flip-flop on the FPGA. So if you think about it, if you've got this huge array on your front panel, you can quickly use up all the FPGA resources because all that data is going to use up a bunch of flip-flops on that FPGA. And this is one of the #1 things that's going to take up a lot of space on your FPGA. So one of the best optimizations that you can do is if you look at your code and you've got huge arrays that contain lots of data on your front panel, you want to get rid of those. One way that you can get rid of those is you can replace them with FIFOs or memory items. And that's something that we'll talk about a bit more in the lesson on sharing data on FPGA. So just remember that for now. The key thing is huge arrays on your front panel are going to eat up all the space on your FPGA. So let's talk about bit packing Boolean logic. So each control, like we said before, is going to have overhead in addition to the size of the data type. Okay, so each control you have there is going to take up some space on your FPGA resource because it's going to have to implement FPGA resources to handle the communication between the FPGA and the host. So if we look at this example here, we've got 8 Booleans, and for each Boolean that you see there, it's going to have to implement a resource to communicate that data between the FPGA and the host. So one way we can save some space is we can use fewer controls, but communicate that same information. So if you look on the right, what we've done is instead of using 8 separate Boolean controls, we're just going to use an 8-bit unsigned integer to represent those Booleans. So for example, if you have the number 255, that's going to represent 1111, 1111 in Boolean. So because we only have one control there, it's going to use up less resources on our FPGA, but we can actually indicate the same information with that data type, right? So if you take that numeric, use the function to convert the number to a Boolean array, and we index that array, we can get that same Boolean information out programmatically. But this way we save space on the FPGA. So in general, if you want to save space on your FPGA, what you can do is use the smallest data type that you need to implement your functionality. So let's take a look at this example here. So if you look on the left, we've got a case structure, and if we look at the data type for that, it is a unsigned 32-bit integer. Well, if you think about it, you probably don't have 2 to the 32 cases in your case structure, right? You probably have like 10 to 20 and something like that. So if we look on the right, we've optimized that, and we're using an unsigned 8-bit integer. So now our case structure is only handling the numbers from 0 to 255. So chances are you have less than 255 cases in your case structure. So in this case, we're saving some space because we're using a smaller data type. A U8 is going to be something smaller than a 32-bit number, right? So on this slide, we're going to talk about coercion. If we look at that top example, we've got some code that's generating U32 data, and then we're sending that data to a I16 indicator, and we see that we have a red coercion dot. Okay. If you see any coercion dots, what's happening is the compiler must determine the proper data type, and it can lead to inefficient data conversion. So instead of leaving it to chance, it's better to specify that actual conversion. So if we look at the bottom, what we're doing instead is we're taking that code that's generating U32 data, we're explicitly using a function to convert that data type into an I16 data type, and then sending it to the indicator. And notice at the bottom, we don't have any coercion dots. So in general, if you want to make sure everything is going to be optimized, try not to use any coercion dots and implement that coercion yourself using functions. And that will generally lead to more efficient implementations. So now we're going to talk about avoiding large functions. So on the FPGA, not all functions are equal, meaning not all functions are going to take up the same amount of space. So for example, we can take a look at these two block diagrams, and they're both trying to do the same thing. They're both trying to divide by 4. So let's take a look at the quotient remainder function. So if we use this on a FPGA, we're taking x and we're putting into this function, dividing by 4, and getting the quotient. So on the right, we're doing the same thing, but we're using a scale by power of 2. So if you're taking x and you're scaling it by the power of 2 to the negative 2, mathematically that's the same thing as dividing by 4, and we get our quotient. So functionally they're the same, but in terms of how many resources it takes on the FPGA, it's going to be vastly different. So if you look at the quotient remainder function, this is a very large function. This is going to take up a lot of resources on your FPGA because the way that it's implemented, it's going to have to figure out the quotient and remainder for a variety of things, and it's going to take up a lot of space. So if you look at the scale by power of 2, in the FPGA world, when you're scaling by a power of 2, it's a simple bit shift. It's not going to take any resources on the FPGA to actually implement that. So dividing by 4, it's a lot more efficient to use the scale by power of 2 function instead. So on this slide, we're talking about the quotient and remainder function. So again, the quotient and remainder function is going to take up a lot of resources. For each operation, it's going to have to implement resources to figure out what the quotient is and what the remainder is. So there's additional resources consumed for that, even if all you're looking for is the quotient. So if we look at these two block diagrams, one common place where people would use a quotient and remainder function when they don't need to is they're trying to implement some sort of counter on their loop. So if you look at that top one, what the user is trying to do is they're just trying to make the output of that quotient and remainder go from 0 to 9. So it's just going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then go back to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So this implementation, because it uses the quotient and remainder function, is going to take up a lot of space on the FPGA. One way you can save some of that space is you can implement it without using the quotient and remainder function. So if we look at our bottom block diagram, instead we're using a shift register and we're initializing it with 0, and then we're going to compare that with a greater than function to 9, and then we're going to output that to a select function. So essentially what's going to happen is the first iteration, it's going to output a 0. It's going to add a 1 to it. So the next iteration, the select function is going to output 1. And the next iteration, it's going to output 2, 3, 4, 5, 6, 7, 8, 9. And then once that number gets greater than 9, this functionality that we've implemented is going to reset it back to 0. So the select function will output 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it's going to go back to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the bottom implementation, we're using different functions to implement that same functionality. However, it's going to be taking up a lot less resources on the FPGA. In this slide, we're going to talk about the scale by power of 2 function. If we were using a scale by power of 2 function, and the input for power is a control, then it's going to take up a lot of resources on our FPGA. The reason for that is if the input for power is a control, then it's going to have to implement logic on on the FPGA hardware for all powers, all possible powers coming from that control. However, if you wire a constant to that input, to the power input, the function consumes no space on the FPGA because all the FPGA is doing is a simple bit shift. So the scale by power of 2 is a very useful function if you ever need to divide by a power of 2. So for example, if we look on the left, we're using the quotient and remainder function, and it's trying to divide something by 4, but because it's using the quotient and remainder function, it's going to take up a lot of resources on the FPGA. Now we can change that and make it a lot more efficient by using the scale by power of 2. So we're just scaling it by a constant of -2, which is mathematically dividing it by 4 to get our quotient. And that's going to consume no space on the FPGA because it's a simple bit shift. So in general, we see that when you're writing some logic, when you have to implement it on hardware in the FPGA, there's some extra considerations that you have to make, because if it's being implemented in hardware, the consequences of that function could possibly take up a lot of space, or it could take up less space.